Everyone, welcome back for 1.5. In 1.1, we solved linear equations, and in 1.3, we solved quadratic equations. And we're just going to talk about almost every other type of equation that we could possibly solve at this level. So a lot of it's going to use things like solving linear equations, things like splitting apart multiple linear equation factors into multiple answers. But in general, we're going to be talking about quite a few different types. So in a way, 1.5 is kind of like a showcase. You already see all the different types of things that we're going to learn to solve here, like factoring, rationals, radicals, rational exponents, and quadratic likes. So there's a lot going on here. Take each subsection as kind of its own actual subsection, but how we solve each one is very different. But again, what we're going to use is a lot of what we have talked about in 1.1 and in 1.3. One thing I want to stress before we do any of these is that, in 1.1 and in 1.3, I said, make sure you check your answers. And in 1.1 and 1.3, linear and quadratics, you don't really have that problem, really. Whatever answer we get is going to be the right answer. But what you're going to see here in 1.5 is that it is possible for us to get what are called extraneous solutions. Solutions that we get when we apply a certain algebraic method, but when you go back to plug them in, they don't actually work. So you're going to see me check a lot of answers here and say like, oh, look, this answer doesn't work. So just in general, I've been saying it for a while here in chapter 1, but please check your answers when you are doing these types of problems. So let's get into the first type. Let's talk about factoring. And we've kind of been doing this. We've factored quadratics before. Well, all we're going to say here is if we can factor the thing, we can solve it just like we've solved anything else. So again, if we can factor it, we can solve it. So let's say we have x cubed plus 3x squared equals 4x plus 12. And what we're going to do here to solve this, let's bring everything to one side. So let's subtract 4x on both sides. Let's subtract 12 on both sides. Okay, and now what we have are four terms whose collective greatest common factor is 1. That was usually a really good heads up for us to do factoring by grouping. So let's factor the first two. Let's factor the second two. We see here in the first two, we could take out an x squared. In the second pair, we could take out a negative 4. Oh, well, they have x plus 3 in common. We can factor out x plus 3. And then everything that's left over, right? P4, us factoring. Well, we also know that x squared minus 4 is also x plus 2x minus 2. And now from here, this is actually pretty nice. What we had in 1.3 was two factors that were multiplied to 0, and we set each factor equal to 0. Well, we can extend this to however many factors we have multiplied equal to 0. We could set all of them equal to 0. And now from here, these are all just linear equations. Subtract 3 on both sides, subtract 2 on both sides, and add 2 on both sides. So we get 3 answers. Now, maybe there is some sort of pattern where the fact this is x cubed, we had 3 answers. Maybe x to the 4th would have 4 answers. And we're not going to really broach as to how or why that is the case until chapter 3. So, don't be looking necessarily for 3 answers if you only get 1 answer, right? There is a theorem to this, but we're not going to talk about that theorem for a while. But there we go. Really no different from quadratics. It was factor and set each factor equal to 0. And the only difference is the factoring was a little different, and we had 3 answers instead of 2. So factoring, just factor the thing, right? So x to the 4th equals 9x squared. Same thing. Let's get everything to one side. So let's subtract 9x squared on both sides. All right, well, these two things have x squared in common. So let's factor out x squared. Then x squared minus 9. We can make that x plus 3x minus 3, difference of squares. And now we again have 3 things that are multiplied to 0. So let's set each one equal to 0. Well, x squared equals 0. The only location where that is 0 is 0. X plus 3, let's subtract 3 on both sides. X minus 3, let's add 3 to both sides. And we again get 3 answers. So last one was x cubed. We had 3 answers. This one is x to the 4th. We have 3 answers. So like I said, don't look for patterns right now. We'll talk about what that pattern is in quite a while. And it's several videos. We have an entire chapter 2 to get through. Okay, but what I want to make sure is that you don't do this. What you are very tempted to do is that you just divide both sides by x squared. Oh, right, we can divide numbers. We can divide x squareds. So you divide x squared on both sides, and x squared cancels out. X to the 4th over x squared is just x squared. And then you take the square root of both sides. You get plus and minus square root of 9, which would give us x equals plus and minus 3. But here's the problem. The answer we had in the previous slide had 3 answers. For the exact same problem, one of them was 0. But when you take the square root of both sides like we just did, you only got 2 answers. So there's a larger issue at play here where if you divide by x squared, what you're essentially allowing is that you divide by 0, right? X equals 0 is an answer. Well, if x is 0, then you just divided by 0 squared. And at no point in this class, and no point in almost any class, will you ever really broach the topic of dividing by 0 in a meaningful way. We know that anything divided by 0 is undefined. So don't divide by variables, only divide by numbers. Okay, so again, factoring, always go for factoring. Do not try and divide by variables or x's. Okay, so factoring, there's really not a whole lot to say there, right? If you could factor it, you can do it. But let's get into all other different types of equations, things that we have worked with before, but maybe not necessarily have solved before. Okay, so let's do some rational equations. And rational equations, well, rational numbers are numbers that are fractions. Rational equations are just equations that are fractions. So we have 1 over 6 plus 1 over x plus 1 equals 1 over x. And what we're going to do, the method to solve rational equations is to multiply everything by the least common denominator. We spent a lot of time in P5 talking about least common denominators. You know how to do it with numbers, and we talked about how to do it with variable terms. So let's multiply everything by the least common denominator. In our case, let's look at all the denominators we have. 6, x plus 1, and x. Well, I know x plus 1 and x look a lot alike, but as factors, they don't have anything in common, right? If x is 2, then this is 2, and this is 3. So 2 and 3 don't have anything in common. So instead, multiply everything by the LCD. Our LCD would be 6 times x plus 1. And we're going to multiply it on both sides. Now, there's kind of an issue here that is very similar to that last issue I talked about in factoring, but what we're going to get is something a little different in what we did for factoring, that very last, don't do this example. What we got in that case is you lost answers, but maybe we get something a little different here. So let's distribute this least common denominator to each and every numerator, right? This is like an imaginary 6x, x plus 1 over 1, and then it just becomes fraction multiplication. 6x, x plus 1 times 1, 6x, x plus 1 times 1, 6x times x plus 1 times 1. And now what you probably see is that some things cancel out. How nice. 6 cancels out here. X plus 1, the whole factor cancels out here. And x, that cancels out here. Oh, that's really, really nice. Cool. All righty. From here, we can distribute x. We can distribute 6. We can combine x and 6x. If you have 1 apple and I give you 6 more, you now have 7 apples. Let's bring 6x plus 6 to the other side. Let's get everything to one side. So let's subtract 6x and 6 on both sides. Well, 6x minus 6x, that goes away. 6 minus 6, that goes away too. That's the whole point. But here, you have 7 apples, and then I take 6 more of them away. Now you're back to 1 apple, and now we're here. And wow, look at that. We have a nice, very pretty, factorable equation. So we factor x squared plus x minus 6 to x plus 3x minus 2. Again, go back to the P4 video if you want to see practice on how to factor. And now set each one equal to 0, and we get x equals negative 3 and x equals 2. So 2 answers. Okay, nothing weird happened in that question, but I already told you that something weird still might happen. Let's see. All right, 1 over x minus 1 over 5x plus 10 equals 1 over 5. Well, before we try and determine what the least common denominator is, I've been preaching factoring for so long. Let's factor this middle term. We can pull out a 5. Okay, well, now we're still going to multiply by the LCD, but notice that we don't need to multiply by 5 twice, right? This 5 is here, this 5 is here. Okay, we got to multiply by a 5 to everything, multiply by an x, multiply by an x plus 2. So you could have multiplied by x times 5x plus 10 times 5. Your numbers would be just a little bit bigger, maybe a little bit weirder to deal with toward the end. So again, factoring saved us from needing to multiply by an extra 5. Okay, well, put all this into the numerators. And now I didn't really stress it in the last example, but notice something. The reason we multiply everything by the LCD is so that we get rid of the fractions. In general, fractions, scary. We don't like dealing with fractions. So what is instead quite nice is by multiplying everything by the LCD, all the fractions go away. And that's the benefit to multiplying everything by the LCD. So here, x is going to cancel out. Here, x plus 2 and 5 is going to cancel out. And in the last one, 5 is going to cancel out. So again, the method of multiply everything by the LCD is very nice because it gets rid of all of the fractions. The less fractions we need to deal with, definitely the better. All right, let's distribute a 5. Let's distribute an x. 5x minus x is 4x. And let's bring everything to the right-hand side. So let's subtract 4x on both sides. Let's subtract 10 on both sides. 2x minus 4x, you have $2 and you spend $4. You are now $2 in debt. And this doesn't factor, but you know what? Why not? Let's do some more quadratic formula practice. A, if this is ax squared plus bx plus c, a is 1, b is -2, and c is -10. Quadratic formula looks like this bad guy right here. And let's plug in everything we know. B is -2, B is -2, A is 1, C is -10, and A is 1. Alrighty. -2 is +2. -2 squared is +4. -4 times 1 times -10 is +40. 4 plus 40 is 44. We can rewrite square root of 44 as square root of 4 times 11. Square root of 4 is 2. And now we can divide both of these by 2. We can, in a sense, distribute the parts of the numerator with the denominator. So 2 over 2 is 1. 2 squared 11 over 2 is 2 square root of 11 over 2. And, I wanted to do this just to make sure that you don't try and cancel out just one of these 2's. Don't forget, we can only cancel things out when everything is multiplied or divided. So, just very briefly going back to what we had here, we were able to cancel out x because it was 5 times x times the factor x plus 2. That's why we could factor out x. 5 times x plus 2. 5 times x plus 2. That's why things can cancel out. So there is a little bit of a reason why we are able to do these things. So again, don't just try and cancel out one of the 2's. You're dividing both of them by 2 because we got this plus and minus up here. Well, 2 divided by 2 is 1. 2 divided by 2 is also 1. And we're left with just square root of 11. Okay, so maybe still nothing weird. I might have misremembered when the weird things happen, but I swear they do happen. Maybe it happened. I think it happens in this one. So far, nothing really weird, right? We got answers that worked out nicely. You should be checking the answers on your own. I don't want to spend time just plugging in answers unless there's a problem, show you something new. So let's do it again here. All right, we're going to multiply everything by the LCD, but instead of trying to multiply everything by x minus 1 times x plus 3 times x squared plus 2x minus 3, well, it's really nice that we could factor and see that, oh, look at that. This has an x plus 3. This has an x plus 3. This has an x minus 1. This has an x minus 1. Multiply everything by x plus 3, x minus 1. Okay, all righty. Well, here again, let's distribute all of these to numerators. So x plus 3x minus 1 times 1, x plus 3 times x minus 1 times x this time, x plus 3x minus 1 times 4. And now you see things cancel out. X minus 1 goes away. X plus 3 goes away. X plus 3 and x minus 1 goes away. And now we're back to just a regular equation. If you multiply everything by the LCD and things don't cancel out, you might have done something wrong. You might have chose the wrong least common denominator. So either one, you don't do it right the first time and you accidentally make a mistake, or two, you didn't multiply by enough. And all you would need to do is just multiply by a little bit more. You can do it in 2 steps. That's fine. Just make sure that if you are multiplying and canceling things out, you're doing that part correctly. Okay, now that we're back to a regular equation, let's distribute this x. Then let's combine some like terms. X minus x. Oh, well, that just goes away. We can subtract 4 on both sides to get 0 on one side, right? We like having 0 on one side. X squared minus 1 factors to x plus 1, x minus 1, and we set each factor equal to 0, and I think we're pretty okay on that part. So we have 2 answers, right? Everything we've been doing so far, we've had 2 answers for rational equations. That is, to an extent, a coincidence for the types of rational equations we're looking at. But yeah, both are answers, right? We haven't had any problems so far. But very large BUT. Okay. Well, if you don't see it right away, let's go in and check our answers. Well, I'm going to let you check x minus 1 on your own, but let's check x equals 1 together. When we plug in x equals 1 back into our equation, we plug x equals 1 here, 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 and here. And what you see is 1 minus 1 and 1 minus 1. Well, 1 minus 1 is 0. 1 minus 1 is 0. 0 times anything is 0. So we have 2 of our 3 fractions that when we plug in x equals 1, we get something that is undefined. And that is not allowed. So going back to what I mentioned way back in the beginning of the section is that we sometimes get these things called extraneous solutions. That we've been doing this algebraic method of multiplying everything by the LCD. But when we did that, even though it worked 2 of the times, this 3rd time that we did it, we got answers that didn't work out nicely. Or not, I wouldn't say didn't work out nicely, but they caused problems. They're not in the original equation's domain. We've kind of brushed domain so far. We're going to talk more about domain in 2.4, but look at the original denominators. You were never allowed to have 1 here. You were never allowed to have -3 here. So make sure when you check your answers that you don't run into problems like this, where 1 over 0 is literally undefined. 4 over 0 is undefined. X was never able to be equal to 1. X was never able to be equal to 1 to begin with. So x equals 1 is extraneous. It doesn't count. The only solution is x equals -1. So for the first time here in chapter 1, it is justified that I say check your answers. You should be checking your answers for everything just to see if you get answers that make sense. Or just to make sure your answers are right, I should say. But, we run into very bigger problems sometimes, especially here in 1.5. So even though we got 2 solutions algebraically, only one of them is true when you go back to plug it in. Okay, let's do another one like that. X over x minus 1 minus 1 over x plus 1 equals 2x over x squared minus 1. All right, rhyme and reason. Let's factor, and you see the least common denominator is just the combination x plus 1, x minus 1. Everything that we would need to cancel out every denominator. All right, let's distribute x plus 1, x minus 1 to each numerator. And now what you see is a bunch of things cancel out. X minus 1 goes away, x plus 1 goes away, x plus 1 and x minus 1 goes away. Now we're back to a normal equation. Let's distribute x. Let's distribute a -1. X minus x goes away. Let's subtract 2x on both sides. And now we get something that factors to x minus 1, x minus 1. Set each one equal to 0. Oh, and we actually only get one solution this time. And that's just a quirk of what the question was. but it's possible. It's possible you get an answer that happens twice. There's nothing wrong with that. It just means there's only one answer, just like it happened in 1.3 sometimes. But okay, and maybe you see what's going to happen next. Let's check x equals 1. And we actually run into the exact same problem that we had before. When we plug in 1, 1 minus 1 is 0, and 1 squared minus 1 is also going to be 0. Oh, look at that. X equals 1 is extraneous. That's a problem. But one thing that's weird here is that in the last question, when we had an extraneous solution, we had two answers, and one of them was extraneous, so the other one was the answer. But here, we have x equals 1 is our only solution, and our only solution is extraneous. Well, that just means there's no solution. So if your only potential answer doesn't work, that's okay. It doesn't mean that like, oh, well, it's the only answer. It has to work. No, it's possible that there is no solution to the equation. And that's very much okay. So don't be afraid to say that all of your solutions are wrong. I mean, if all of your solutions are wrong because you got the wrong possible solutions, that's one thing. But it is entirely possible that there just is no solution to an equation. Okay, we carry on. So that was rational equations. And what we're going to talk about next are radical equations, or, totally radical equations. Don't laugh at that. That wasn't funny. But radical equations are, you guessed it, equations that have radical signs. That's it. Okay, here's what I want you to think about. When we are doing regular, polynomial equations, like quadratic equations, we talked about how if we have x squared equals a number, we can take the square root of both sides. Well, that means that x to the 2, the way we undo x to the 2 is to take the square root of both sides. Okay, well, if we have x cubed, the way to undo x cubed would be cube root of both sides. Well, how do you then undo square root or cube root or fourth root or fifth root? Well, you guessed it. The way we undo roots are by raising both sides to that power. That's it. All right, so all we need to do is raise both sides to the third power. Same way as square root cancels out x squared, kind of, right? There are some quirks there, but same way that cube root, the same way that square root cancels out squared is the exact same way that cubing both sides cancels out cubed. All right, well, so cube root and 3 go away. We're left with just the inside. 3 to the 3 is 27. And now we're just back to a linear equation. Subtract 6, divide by -3, and we get x equals -7. Nice. That's it. All right, well, what if we have cube root of -3x plus x equals -3? Well, is it a problem that we got a negative on one side? I don't know. Let's see what happens. Well, we cube both sides again. Inside is just -3x plus 6. Right side, we now get -27. And we subtract 6 again, and we divide by -3, and we get 11. Oh, there's nothing wrong with there. Don't forget, way back in P6, we said cube roots, odd roots, can produce negative numbers, right? Cube root of -27 is -3. The problem arose when we were doing even roots. For example, square roots were never equal to negative numbers. Fourth roots were never equal to negative numbers. So it is a little different depending on the root. If your root is odd, it's okay that you have negative numbers on one side. There's nothing wrong with that. But maybe something is weird when we have even roots. Let's think about that. All right, so we have fourth root this time. Does that mean we completely change how we solve this problem? No. So last one, we had cube root. We raised both sides to the fourth power. Guess what? we're just going to, sorry, last question was cube root. We raised both sides to the third power. This one's fourth root. We're just going to raise both sides to the fourth power. Again, fourth root and to the fourth cancel each other out. Negative 3x plus 6 equals 3 to the fourth, which is 81. Subtract 6 on both sides. Divide negative 3, and you get negative 25. Absolutely nothing wrong there. Well, let's try and do the exact same thing, but with fourth root of negative 3x plus 6 equals negative 3. And you notice that the slide doesn't have as much info on it because, this is all the way right here. But there's no solution because even roots can't produce negative numbers. You could absolutely try and solve this. What you would get is the exact same solution as before, right? If you try and did everything, but this is negative 3, well, negative 3 to the fourth is also positive 81. So you do all this work, you would get x equals negative 25. But when you plug negative 25 into here, negative 3 times negative 25 is 75, positive 75. Positive 75 plus 6 is 81. Fourth root of 81 is positive 3, but we're saying it's equal to negative 3. However, we can treat it far easier and just say that even roots can't produce negative numbers. Done. That's it. Okay, let's keep going. Fifth root, well, I think you guys get the idea, right? We can mix and match, what we put inside the root and what we put on the outside. But the idea is it doesn't, all the steps are still going to be the same. Only thing that changes is that we raise both sides to the fifth power instead. But from here, again, it is really no different. So again, I'm keeping the inside consistent. I'm keeping the outside mostly consistent. I'm just trying to show that depending on the root, that's all we're going to raise both sides to. Nothing too fancy or too weird. Okay, well, what if we let one side be just a variable? Okay, let's see what happens. Here we have x equals square root of 6x minus x cubed. Here we have square root. So how we undo square root is by squaring both sides. Well, x squared is just x squared. Square root and squared cancel each other out. All right, well, this is just a linear equation. Or not a linear, a regular equation. Let's bring everything to one side. I'm going to bring everything to the left. If you want to bring everything to the right, that is not wrong. You'll get the exact same answers. Let's subtract 6x and add x cubed on both sides. So here, we're a little jumbled. Let's just rewrite terms in order. And now, let's see what happens. Here, we can factor out an x. And, this is also nice, easy, and factorable. And now we're just back to an equation with 3 factors. Set x equal to 0, set x plus 3 equal to 0, set x minus 2 equal to 0. While x equals 0, no work to do there. Here we can subtract 3. Here we can add 2. And we get 3 answers. So we're done, right? 3 answers. No big deal. We haven't run into any problems with checking answers before, have we? Maybe we should check our work. You can take a second and think about which one might be the problem. But let's try negative 3. Well, we plug in negative 3 and, we get a square root. We get an even root equals a negative number. Square roots can't produce negative numbers. Even roots can't produce negative numbers. So negative 3 doesn't work even if you wanted to. 6 times negative 3 is negative 18. Negative 3 cubed is negative 27. Negative 18 minus negative 27 would be negative 18 plus 27. And negative 18 plus 27 is 9. Square root of 9 is not negative 3. So our only answers are x equals 2 and x equals 0. So, you might not always need to plug in everything, but the second that you run into problems that very generally, have like domain issues, right? Like square roots can't produce negative numbers. Cube roots different. But for example, here, we get right away that we can't have a negative outside a square root like that, or equal to a square root, I should say. And like for the other ones, for rationals, we couldn't have 0 in the denominator. So just look out for things like that. Beyond just, does my answer, when I plug it in, does it actually work, numerically? All right, well, here, let's do it again, but we have negative x equals square root of 6x minus x squared. So right away you say, oh, negative x, square roots can't produce negative numbers. So we're done, right? Let's see. Let's square both sides, right? This is square root, so let's square both sides. Negative x squared would be positive x squared. Square root and x squared cancel out. All right, well, let's see what happens. Let's bring everything to the left-hand side. I'm going to add x squared and subtract 6x again. Well, here we get x squared plus x squared, that is 2x squared. 2x squared minus 6x equals 0. We can factor out a 2x. This is now two separate factors multiplied to 0. We can divide 2, add 3, and we get 2 answers. And let's see what happens. Well, if we plug in 3 again, oh, would you look at that? We're left with a negative 3 equals square root of some answer. Also, I don't know why these are cubed. These should be squared. That's a mistake, but it doesn't change the problem at all. Square root still can't produce negative numbers, so we don't run into an issue. Well, we run into an issue, but it's an issue we can easily pick up. When you plug in 3, we get no solution, but notice that 0 is totally okay. So don't be afraid of having negative variables on one side, right? Negative numbers, there's nothing you could do about that. Either it's positive or it's negative on the outside. But when it's variables, we have to treat it a little differently. So just be on the lookout for that. All right, let's do x equals cube root of 6x minus x cubed. Well, this is cube root, so let's cube both sides. X cubed equals 6x minus x cubed. Well, we can bring everything to one side. I'm going to bring it all to the left-hand side. Only difference here is that we now have 2x cubed. Well, we can still factor out a 2x, and we get x squared minus 3 on the inside. Well, let's set each one equal to 0. Here, we're just going to divide by 2, no big deal. But here, let's add 3 to both sides. Let's take the square root of both sides. But don't forget, when we take square roots of both sides, we get plus and minus square root of that answer. So we get 3 answers. Go back and check them on your own, but there are not any issues here. Okay, finally, we get one that all of them work out. So, okay, let's do another one. Why not? I don't remember how many solutions there are or how many questions there are. That's fine. Same thing. We got negative x on the outside, cube root. Let's raise both sides to the third power. But here, negative x cubed would be negative x cubed. Let's again bring everything to one side, but I'm just going to add x cubed this time. I'm not going to bring everything. Let's just add x cubed to both sides. And we did that because, oh, look at that. That's just going to go away. That's pretty nice. Oh, and we only get one answer this time. Just dividing 6 on both sides will give us x equals 0. So that's an interesting problem. Okay. Kind of weird. That's fine. So lots of different examples. But what happens as soon as we have something like this? And what I mean by this is we got a square root and then an extra plus 1 on the outside. Well, one thing I want to stress is this. Every single problem we've done so far has been just that root on one side by itself. And you can immediately jump to squaring or cubing or to the fourth of both sides. But the second that the square root or whatever radical is not on its own, you need to get it on its own. You cannot square both sides when it is like this, because if you were to square this, this is a plus b squared, and that would be something you need to FOIL. And it wouldn't even get the square root out of there if you had to FOIL. So please be careful. When you are dealing with radical equations, make sure the radical is by itself. So all we're going to do here is subtract 1 on both sides. And now we can square both sides to get rid of the square root, but notice this. this isn't just a plain number. This isn't just a single variable. X minus 1 squared is x minus 1 times x minus 1. This requires foiling. So very different from when there's only one thing on one side. Only one thing on one side, you raise it to the third power or whatever, and you're done. But that's not what happens here. This requires us to FOIL x squared minus x minus another x minus 1 times negative 1 is plus 1. Let's combine like terms. And now we can solve it like, a regular single equation, but we had to make sure that we did that foiling part. So please don't forget rules of algebra. Don't forget rules of multiplying polynomials that we did all the way in P3. If you forget stuff like that, you're going to be in trouble. Let's bring everything to one side. Let's subtract 2x. Let's subtract 1. All right, after we combine, 1 and negative 1 goes away. Negative 2x and negative 2x becomes negative 4x. And now from here, factor out x, set each one equal to 0. We get 2 solutions. All right. Well, what would this problem be without an extraneous solution? Which one do you want to plug in? I don't know. Let's plug in 0. Let's try what happens when we plug in 0. Well, 2 times 0 is 0. 0 plus 1 is 1. Square root of 1 is 1. And then 1 plus 1 is 2. But 2 doesn't equal 0. So this is actually an even different type of problem, and a problem that you might run into more if you just get the wrong possible answers. So beyond just, we can't have square roots of negative numbers, and square roots can't produce negative numbers, and we can't have zeros in the denominator, it's possible you get one that just doesn't work out nicely for this type of reason, where when you plug it in, both sides literally just do not equal each other. And that is totally okay. There is nothing wrong with that. So x equals 4 is our only solution, because plugging in x equals 0 does not work for us. All right, well, kind of similar. Here we have square root of 5x squared minus 10x plus 9 with minus 2x plus 1 on the outside. Same thing. We need to get the root by itself. So let's add 2x to both sides. Let's subtract 1. And now we can square both sides. But this is, again, foiling. It is not just say 2x squared minus 1 squared. No. This is 2x minus 1 times 2x minus 1. So let's FOIL that. 2x times 2x is 4x squared. 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x. Negative 1 times negative 1 is positive 1. Negative 2x minus 2x is negative 4x. All right. Lots of adding and subtracting on both sides. Let's subtract 4x on both sides. Add 4x. Subtract 1. All right. 5x squared minus 4x, 1x squared. Negative 10x plus 4x, negative 6x. 9 minus 1 is 8. Oh, that actually worked out pretty nicely. It's almost like this is a presentation problem. Factor, set each one equal to 0, solve each one, and we get 2 answers. And I think both of them work out. Yeah, how about that? All right. One more crazy example. You're not going to see one like this all that often. But what if we have 2 roots? Oh no, the world is going to end, it seems. Don't worry. When you have multiple roots, what our goal is here is to get one root by itself first, and then we're just going to need to do the process twice. So here's what I mean. Let's add square root of x minus 1 to both sides, so that square root of 2x minus 1 is by itself. Well, what we're going to do is square both sides to get rid of this root. It's not going to get rid of this root, but that's okay. All it means is we're just going to need to do this twice. So let's square both sides. And again, this square root and squared goes away, but 1 plus square root of x minus 1 is foiling. So that square root cancels out. And now let's FOIL. 1 times 1 is 1. 1 times square root of x minus 1 is square root of x minus 1. Square root of x minus 1 times 1 is square root of x minus 1. Square root of x minus 1 times square root of x minus 1. Oh, Square root of anything times itself is just itself. Square root of x minus 1 plus itself is going to be 2 of them, right? If we're multiplying them, square root of x minus 1 times square root of x minus 1, it's just itself. But when we are adding, it is 2 of them. Be very careful. All right, so lots of simplification we can do here. 1 minus 1 goes away. Let's bring this plus x to the left-hand side. Let's subtract it on both sides. 2x minus x is just x. And now the root is mostly all by itself. What you can do is you can divide by 2 and then square. But what you'll see is when everything is multiplied together, it's actually okay for us to square it, right? Because if this was 2 plus square root of x minus 1, well, then we would need to FOIL. But 2 times square root of x minus 1 is just 2 squared, which is 4. Square root of x minus 1 squared is just x minus 1. Here, we got a FOIL on the left-hand side. X times x is x squared. X times negative 1, negative x. Negative 1 times x, negative x. Negative 1 times negative 1, positive 1. And distribute 4. All right. Combine like terms on the left. Negative x minus x, negative 2x. Let's subtract 4x on both sides. Let's add 4 to both sides. Negative 2x minus 4x, negative 6x. 1 plus 4 is 5. Factor, set h1 equal to 0. And we get 2 answers. So radical equations, not so totally radical as I had in the beginning. They can get kind of messy, but they end up kind of all being similar situations. All right, let's get out of radical equations and let's start talking about something a little different. Okay, so let's talk about rational exponents. Now, rational exponents are just fraction exponents, right? Rational equations, fraction equations. Rational exponents was the end of P6 where we had a fraction in our exponent. So let's say we had something like 3 over 2 as an exponent. Well, in 3 over 2, what that's saying is square root of something, the denominator is 2, square root, but then the numerator was 3, so that's cubing. So basically, numerator is what we're actually doing to the thing. Denominator is what kind of root are we taking. And we're going to use a lot of that today, or in this subsection. So say we have some expression u to the a over b equals c. Well, kind of think about this. When we were doing square roots, we squared both sides. And when we're doing squared, we square root both sides. And we know square root is like 1/2. So what we're going to do is something very similar, except instead of trying to think about it in terms of roots and cubes and all that, what we're going to do is just raise both sides to the reciprocal power. However, we need to keep something in mind, that if we raise both sides to the reciprocal, what the value of a is matters. Because think about this. If this is 3 over 2, we're raising both sides to the 2 over 3. When we raise both sides to the 2 over 3, that's saying take the cube root and then square it. But if this is 2 over 3 and we raise both sides to the 3 over 2, that's like saying take the square root of both sides and then cube it. But remember what happens when we take square roots of both sides. So what this ultimately boils down to is this. All right, so if this original numerator is odd, nothing weird happens. You raise both sides to the reciprocal power, so you raise both sides to the b over a. That gets rid of it for u, just like square roots and squared, it just gets rid of that. But on the other side, you get c, whatever that constant is, to the b over a. And I've already told you that to the b over a is basically saying 8th root raised to the b. But if a is even, well, we pick up an extra plus and minus. Again, if this original numerator is even, let's say 2, that means that when we raise both sides, the 2 ends up in the denominator, but that is like taking a square root. So, again, long story short, if original numerator is odd, nothing weird happens. If original numerator is even, pick up a plus and minus. So you could take these two things as a rule. If a is odd, raise both sides to the reciprocal, and then do, denominator, new denominator, raised to new numerator, and same thing here, but when it's even, plus and minus. All right, maybe that's kind of wordy, kind of complicated. Let's do a bunch of examples. X to the 3 over 5 equals 8. So what we're going to do is raise both sides to the reciprocal power. Well, this is 3 over 5, so we're going to raise both sides to the 5 over 3. Okay. But now what we need to look at is this original numerator of our exponent. If the original numerator is even, we pick up a plus and minus. But if the original numerator is odd, nothing happens. So original numerator even, plus and minus. Otherwise, no. Okay, well, this original numerator is 3, and 3 is odd. So we do not pick up a plus and minus, but we still raise both sides to the 5 over 3. Okay, well, that's so far the new part, but it's been a while since we've talked about rational exponents, so let's look at this a little bit more. 3/5 and 5/3, well, that cancels out. That's the whole point. But what this says is 8 to the 1/3 to the 5, right? Exponent raised to an exponent. We could multiply those exponents to get back to 5/3, but this is like to the 1/3 and then to the 5. Well, to the 1/3 means cube root. Cube root of 8 is 2. 2 to the 5th is 32. So denominator root, numerator power. So this says cube root and then raise it to the 5th. Cube root of 8 is 2. 2 to the 5th is 32. Okay, well, let's do more examples of this. Another thing I want to stress is that, if your rational exponent part is not by itself, get it by itself, just like other things we've done before. In a lot of cases, these things that we want to apply, they need to be by themselves on one side for us to be able to do that. So let's add 30 to both sides. Let's divide both sides by 2. And now we can finally, do the rational exponent step. This is to the 3 over 2. So we're going to raise both sides to the 2 over 3. And again, this original numerator, this 3 up here, can I highlight just that? I did it before. Okay. The original numerator was 3. 3 is odd. Nothing weird happens when it is odd. Okay, so we're going to raise both sides to the 2/3. To the 2/3 says cube root first and then squared. So cube root of 27 is 3 and 3 squared is 9. Oh, but don't forget, the thing that had the rational exponent wasn't just x, and that's okay. So 2x minus 1 equals 9. You know how to add 1 to both sides. You know how to divide both sides by 2, and you get x equals 5. Okay. Well, let's start doing things where things actually start to happen and things that are weird. Well, here, you already see we're going to raise both sides to the 3/2. However, this original exponent's numerator is even now, right? Previous two cases, let me go back to them really quick. Here, this is 3 over 2. Numerator was odd. Nothing weird happened. No plus or minus happened when this was odd. But for the first time, we have an example where this numerator is even. If the original numerator is even, we pick up a plus and minus. Again, when we raise both sides to the 3 over 2, this is like saying take the square root of both sides and then cube it. And we remember from 1.3 that when we are taking the square root of both sides, we pick up a plus and minus. All right, so 4 to the 3/2 says take the square root first. Square root of 4 is 2. 2 cubed is 8. And now we just get two equations. 3x minus 1 equals positive 8. 3x minus 1 equals negative 8. Add 1 to both sides. Divide both sides by 3. And we get two solutions. Okay. So a little messy, but really not all that much of an extra step. I mean, yes, it created two separate problems for us at the end, but I think by now, solving equations like this, we absolutely love. So again, it all comes down to the original exponent. So here, we got to get 2x plus 1 to the 4/3 by itself. Let's add 7 to both sides. And now we're going to raise both sides to the reciprocal of 4/3. That would be 3/4. But this original numerator is even. So if it is even, we pick up plus and minus. So 16 to the 3/4. Okay, 16 to the 3/4 says take the 4th root and then cube it. So 16 to the 1/4, 4th root of 16. 4th root of 16 is 2. 2 cubed is 8. And now we again have two equations. 2x plus 1 equals positive 8. 2x plus 1 equals negative 8. Subtract 1 and divide by 2. And we get two answers. So again, one more time. Original numerator odd, no plus and minus. Original numerator even, yes, plus and minus. All right, let's do two more examples. 5x minus 14 equals 3 over 800. We're going to raise both sides to the 800 over 3. However, original numerator is odd, no plus and minus. So we raise both sides to the 800 over 3. Well, very convenient. 1 raised to any power is just 1. You add 14, you divide by 5. How beautiful. But if the original numerator is even, 800, we pick up plus and minus. But still, 1 raised to any power is just 1. So just two separate equations. Add 14 to both sides. Divide both sides by 5. And you get two solutions. So that's rational exponents. Not really much else we can do with them right now. And maybe we come back to those in a little while. But one more small part, quadratic likes. The thing with quadratic likes is kind of interesting because you will see stuff like this in the future. It's just kind of annoying. You're going to see why in just a second. It requires a very well-seasoned mind to recognize some of these things. I don't think any of these are so obvious that you're going to look at it and be like, oh, yeah, I see it right away. So just getting in the habit of noticing these type of things is definitely the key to doing quadratic likes. But again, you're going to find all sorts of stuff like this. So just keep an eye out for them. So for example, let's say we have x to the 2/3 minus 5x to the 1/3 plus 6. Well, here we have an x to the 2/3, and this is like x to the 2 minus 5 x to the 1 plus 6. Only weird thing is that we have these extra, 2/3 and 1/3. Well, what if we rewrote x to the 2/3 as x to the 1/3 squared? Well, now this is like something squared minus 5 times something plus 6. It's quadratic like x squared minus 5x plus 6. Only thing is that our variable isn't x, it's x to the 1/3. Well, we don't want to just magically substitute x in because that kind of screws up what we're looking at. Instead, let's say x to the 1/3 is u. We like using u to substitute things a lot of the time. If you end up taking Calc 2, you might even come back to u substitution, but that's a long time from now. All right, so wherever we see x to the 1/3, let's instead call it u. All right, well, x to the 1/3 would be u squared minus 5 times u plus 6 equals 0. Oh, well, if I gave you this, you would know to factor. you would know to set each factor equal to 0. But here's the thing. We're saying that u equals 2 and u equals 3, but we're not solving equations that are u. We're solving an equation that had x in the beginning. So we substituted u in for x. However, we're not solving a u equation. We need to resubstitute whatever we substituted in as u. Well, I have it here that u is x to the 1/3. So this isn't u equals 2. This is x to the 1/3 equals 2. This isn't u to the u equals 3. This is really x to the 1/3 equals 3. Now, from here, you know how to solve these equations from the last step. We'll just cube both sides, and we get 8 and 27. And those are our two answers. So quadratic likes just introduce this one like kind of intermediate process of just saying, let's solve an equation that looks very similar, and then just resubstitute in the thing we initially substituted. And that's essentially what quadratic likes are. Okay, this video is probably very long. I don't want to go super crazy into doing this, but here you might also notice something squared minus 6 times something plus 8. Well, u, if we say, is x plus 1 over x, well, then this is like u squared minus 6u plus 8. And you know how to factor this. You know how to set each factor equal to 0. So we have u equals 2 and 4. But if u is x plus 1 over x, what we're really going to get is x plus 1 over x equals 2. X plus 1 over x equals 4. All right. Something like this is way crazy. It's more just, to show you the process. From here, to solve each specific part, you would multiply everything by the least common denominator, x. X squared plus 1 equals 2x. Subtract 2x. Factor. Set each factor equal to 0. You get 1. But for the other one, yeah, this is not nearly as pretty. You do the same thing, and now you have to do quadratic formula. So if you want to watch the whole thing, feel free to slow it down. But essentially, we had 2 separate branched equations, and then we got 3 separate total answers. So just something to keep in mind. Again, you could slow down the video to watch all those steps, but once we've set up each specific part, they become equations that we've already talked about. So that's the end of 1.5. Kind of long, kind of showcase. 1.6 and 1.7 are not nearly as long. What we've done in 1.1 to 1.5 has been equations. We're going to learn to solve inequalities in the next section. And then 1.7 is a nice way of going out. We're just going to introduce absolute values to equations and equations and inequalities. So that's the end of 1.5, and I will see you in 1.6. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.